Okay, we are now recording. And this is where we got to last time. Can I hide this? Hide. Okay. I need to share screen. Sorry, I'm not sharing screen. Share screen. Okay, now everybody should be able to see it. So this is where we got to last time. We finished up CFA. And we discovered we had method bias that we couldn't address, and so we'll control for social desirability bias. We fiddled around with a second order construct down here, system success. And I'm going to go ahead and leave that in for now, just so we can play with it. It's also, we're also going to deal with these first order constructs, because our model here, it includes these, not some second order construct. So we'll play with both. But today, we're going to do causal models. The slides should be available for you. Day 3. Mediation, moderation, and controls. And what we're going to do like before. We're just going to do it. And then we'll come back to the slides and talk about it. Perhaps. Actually, we're going to go back and forth a little bit. Okay. Here's what we're going to do. We can go back and forth. For going from a measurement model to a structural model, remember this is a measurement model, and this is a structural model. Anything that has causal prediction going on, that's a structural model. Whether it's using observed rectangles, or if it's using latent factors, it's still causal or structural model if they're causal paths. So how do you go from here to a causal model? It's not that difficult. Here we go. Let's do this. I'm going to save as. I'm going to save this as causal latent initial. Something like that. And what you do is you delete all the covariances you have with your endogenous variables. So what is endogenous? It's anything that's being predicted. We are predicting system success, perhaps. So we're going to delete those covariances. Our mediators are also endogenous. Our mediators are usefulness and comprehensive use. So I'm going to delete all the covariances that go to those guys. And then I'm just going to reorder stuff, move things around. So grab the fire truck and move your IVs over to the left. And social desirability is a control variable, so it's treated like an independent variable. It's treated like an IV. Useful as a mediator, compuse as a mediator, and then this stuff. See if this will move properly. Yeah, there we go. Your dependent variables, let's move over to the right. You can also rotate the factors around using this rotate button. Click there, zoom out. And you can rotate things around a bit, so it's easier to start drawing lines. There we go. How many people are doing this as I do it? I just want to make sure I don't go too fast. Okay. Yep, I'm using the last file from yesterday. Share your screen too, doing it. Excellent. Okay. I'm just taking the measurement model to a structural model. So, yeah, preparing to do mediation, moderation. So yeah, yesterday we imputed some factor scores, and we can use those as well. I'll show that way. Yeah. We have, I showed you yesterday, let's see, did I close it? Yeah, I closed it. Hopefully people are trying to catch up. I'll open this back up. Data. We created a factor scores, underscore C is what it is, this bootcamp trimmed underscore C. That has factor scores that collapsed all the observed variables into a single score for each construct. excuse me. Let me open that up just as review. I know we were all fairly burnt out last night when we finished this. Come in. Okay, here we go. So at the bottom of our data set here, we have all the factor scores from our latent model, decision quality and information acquisition, including system success, that second order factor, with all the other independent variables and mediators. So we could use those instead of the latent model. We could just drag those in as boxes. In fact, I can just show you in a moment. Say again, sorry? I imputed them, yeah, just so that I'd have them actually for interactions later, so for some moderation. But with our model, we don't even need them, but I'm going to show you anyway because it's a useful thing to know. First, I'm going to do it latently. There are latent causal models, and then there are non-latent causal models. This is a latent causal model. See somebody on chat here. If we have a question from yesterday, rescalar invariance, should we wait? Oof. Nope, let's get it out of the way right now. What's your question about scalar invariance? You're welcome to just talk if you want. Unmute yourself. Hello, hello. If you're talking, you're muted. I'll unmute you. Here we go. LDH, did you have a question?
Yeah, I just posted it. Sorry, I'm just checking.
Oh, you're good. Oops. Okay. What if we can't get past the 0.000 p-value? Then you say you don't have whatever type of invariance it is you were testing, and you list that as a limitation, and then you just have to know that any multi-group tests you do in the structural model are potentially invalid. You can't say with confidence that the differences you observe are due to differences in the relationships. They might be simply differences in the measurement.
Quick question: How do you move the constructs with their items and errors all coming? Mine's moving one by one.
Oh, you have to. You have to click on the balloons or flowers, this bouquet here. I know it doesn't make a lot of sense, but this is their preserve symmetries button. So if you click that and the truck, then you can move things all together.
Thanks.
You're welcome. Okay, I'm going to click on the truck here, move this over. For now, I'm actually going, well, I'm going to delete system success here in just a sec. But if we were dealing with the second order construct, instead of these two first order constructs, we would have all of our prediction go into system success like this, instead of into those first order factors. But since we theorized about first order factors and our first order factors worked in the measurement model just fine, I'm going to delete system success and let the arrows go straight to those first order factors. So you get the single headed arrow over here. You draw the model as you theorized it, including social desirability touching everything, because again, we need to control for its effects. We did observe some social desirability in our model. So just draw your model, lots of arrows, try not to forget any. Now in our theory, our atheoretical theory, everything sort of predicted everything, right? Which is mostly atheoretical. But that's how we theorize it. But because everything predicted everything, if you were to do this in a non-latent model, you would have 0 degrees of freedom. Because you have 0 degrees of freedom, you have no way to know if the way you're modeling it is a good way to model it. Although, I guess, conceptually, mathematically, the way you've modeled it is the best way to model it because everything is accounted for. You just can't address model fit. Okay. So this is not fully identified because it's latent. A latent model has all these extra parameters I could be adding. I could covary the errors. I could draw lines from the observed variables to other places. So we still have probably 400 degrees of freedom here. Great. In fact, I bet we have 478 degrees of freedom. Same as the CFA. But we're going to decrease that a little bit. How do we decide whether to do latent model or non-latent model? Generally speaking, a latent model will always be more accurate. It accounts for the error much better. It accounts for measurement, period. It accounts for measurement. Whereas the non-latent model is just using that one score to represent that whole set of measures. So it is less accurate. You will actually get different values. We teach both because it is much simpler to teach a non-latent model because it's a lot less messy. Also, you would want to use a non-latent model if you're doing something complicated like interactions. So we're going to talk about interactions in a little bit. It's where you cross-multiply every piece of the moderator. I'm going to create another model that is not latent for interaction. Okay, but generally speaking, latent is better. For your particular exercise you guys are involved with right now, you are welcome to use either approach. I believe we taught you non-latent, so go for it. Just be aware of its limitations. Okay. One thing we have to do when we're doing structural models is we have to add error. Because anytime you predict anything, there's error associated with that prediction because you can't predict perfectly. So using this bobblehead icon right here, go ahead and add error to useful. If you click it multiple times, it just rotates around 45 degrees each time. So I'm just going to move it to a handy location. Also add it to comp use. And if you didn't have it on information acquisition and decision quality, go ahead and add it there. You don't need to add it to social desirability. You don't need to add it to anxiety or playful because these are not being predicted. So there's no error associated with them. Yep, just DVs and mediators. Notice though that these haven't been named, so we need to name those errors. You can do that through plugins. Plugins, name unobserved variables. And that will automatically name those error terms for us. Yeah, it's the amount of variance unexplained through the prediction. Yeah, good job. Yeah. One other thing we'll need to do. Because we know decision quality and information acquisition are related, and we're not going to use it as a second order factor, we need to covary their error terms because we know there's going to be a systematic correlation that we're not accounting for. We need to account for that sort of indirectly through their errors. We can do the same thing for useful and comp use if it appears that's a necessity. If you want a reference for when that's appropriate, let me show you. I think we showed this yesterday. Dave Kenny, he has a website excuse me, on measuring model fit, and he talks about when it's okay to covary error terms. This is one of the instances where he says it's perfectly fine to covary the error terms of same leveled, I think is the word he used, same leveled endogenous variables. So we have DVs, they're on the same level. Mediators are on the same level. So he says, okay to covary the DV error terms. may be okay also to covary the mediator error terms. We'll see if it's even needed when we look at model fit. You can, yeah. A lot of people do. I bet he has more citations to that website than I have to my most popular paper. Yeah. People cite my videos. You can cite a video. Yeah, you can cite anything. You can cite conversations. You can cite personal conversations you've had. So you could cite this boot camp if you wanted, or a lunch we had together. Gaskin and 20. No, that would not pass every reviewer. My name does not yet carry that much weight. Yeah. All right. So we're missing one more thing. If we go back to our model here, we haven't added experience. We're not going to do that yet. You can test interactions in a separate model, which we'll do later. We're also missing multigroup. We can add that now unless there are any paths we want to test without the multiple groups. And we'll do that first, and then we'll add multiple groups in a moment. We're also missing our control variables. When do you add control variables? The answer is immediately. You add your control variables from the beginning, and you just leave them in there, and for the most part, ignore them. You're just controlling for their effects. So let's do that. Age and frequency, let's throw in here. So if you click on the stacky thing, the white stacky thing, right there above the closed hand below the bobblehead, then you scroll down to the very bottom, you'll see we have age and experience down in here. And you literally just pull them out, just drag them out to wherever, age and experience. And then close this box. If we'd like, we can, you have some options with controls. There are actually different schools of thought on how to handle controls. Some would say, because you're controlling for it, you need to have it connected to every variable in the model. And that works. It doesn't harm anything unless you're using a path model where there isn't a lot of, where there aren't a lot of degrees of freedom. Some would also say, well, you only need to control for their known or theorized effects. So I'm theorizing that age has some sort of effect on decision quality. The older you are, the better decisions you make. I don't see age being connected to comprehensive use or usefulness at all, theoretically. And so why do I need to control for their effects on those? I'm of that second school of thought. Connect them to what you theoretically believe they should be connected to. And then if model fit says, no, you have to connect it to this one, otherwise you have poor fit, go ahead and add that in just to appease the model fit gods. Okay, here we go. So I'm going to move these guys over to where social desirability is, because it's also a control. And we also need to covary it with these other exogenous variables. Best way to do that, use the pointer finger selector over here and select all of those exogenous variables. And then go to plugins, draw covariances. There we go. Is there a way to get them all on the same side? Yeah. That's all I'm going to say about that. No, you're never going to copy and paste your Amos model into a manuscript. So it can be as ugly as you want. The only reason you wouldn't want an ugly Amos model is for troubleshooting. Eventually it gets so ugly you can't find the problems. But this isn't too ugly yet. Okay. We need to draw regression lines from experience and age to what we think they should affect. Will experience affect usefulness? Probably. Will it affect comprehensive use? Probably. Information acquisition? Definitely. And decision quality? I would say definitely. Is your experience using Excel? It should have an impact on all the outcomes. Will age affect usefulness? Probably not. Age affect comprehensive use? Probably not. But it probably will affect our two dependent variables. I'm going to draw lines from them from age to the DVs. Okay, we now have a testable model. Let me jump on the chat, see if we've missed anybody here. See, not clear the difference of latent model and not latent model. Please clarify. Okay, just a sec. So this is a, where'd it go? This is a latent model. It's latent. Actually, this is a hybrid model because I have these non-latent variables in here, experience and age. But a latent model would be anything with latent factors in it. A latent factor is anything that's being measured indirectly through multiple observed variables. So anxiety, that's a latent factor. Playful is a latent factor. A non-latent model would be something, let me save this real quick. A non-latent model would look something like this, where you just have boxes, nothing unmeasured. It's all measured, it's all observed. There's nothing latently being observed, latently being measured here, just boxes. Notice if I were to run this, you don't have this, it's okay. Oh wait, it won't run because I've moved everything. But if I were to run this, the number of degrees of freedom I have is probably in the order of less than 5, because I've accounted for almost every possible path. Whereas in a latent model, let me go back to our latent model here. Right here. There are so many parameters I could have added, but did not. For example, all the covariances between errors, lines from individual items to other individual items. So many things I could have done. So in this model, I have 400 degrees of freedom plus. So there are error terms in that model, and a few of them are covaried. Yeah. Let me go back to chat. Let's see. You correlate the controls with the independent variables by default? Yes. In Amos, there's an assumption that all exogenous, all non-endogenous, really, variables, like independent variables, are covaried because it's a covariance-based SEM. So all non-predicted variables should be covaried. That non-latent model is based on factor score? Correct. Yeah, I use factor scores for this one. Well, for the non-latent one. From Isaac, no effect of control on exogenous factors? Am I controlling for the effects of experience and age on anxiety and playfulness? I am, because they're covaried. So they will share variance and thereby, to some extent, control for their effects. Use the non-latent model, you use the score you got in SPSS for the latent variables. Correct, yeah, those imputed factor scores we made yesterday. Before you get too far, please, with which model did you begin? The CFA immediately after we completed method bias? Yeah, that's the model I started from. Well, the final CFA is what I started building this from. Okay, yeah. Oh, yeah, sorry. I'm using these fancy variable names, yeah, vocab. So exogenous is anything that has arrows going out of it. Endogenous is anything that has arrows going into it. Now, you may say compuse, that's both exogenous and endogenous. So which is it? By default, if it has arrows going into it, the endogenousness trumps the exogenousness. Yeah, sign that. Wow, I'm impressed. Okay. Okay. Yeah, what we're trying to do with this model is predict decision quality and predict information acquisition, and we're doing it with anxiety and playfulness and compuse and usefulness. To predict, yeah, the 5 on the left, predicting the 2 on the right. And then we're controlling for the effects of these 3 right here. Theoretically, we're not actually very interested in these 3. We're just making sure it's not because of these 3 that we are able to predict. It is. Yeah, we didn't have a latent for age. That'd be kind of funny. How old do you feel? How old do you feel today? Strongly agree. I feel like I'm ancient. And experience, yeah. Okay. Oh, is there an exception to the rule of covariating exogenous variables? Again, different schools of thought on this. In a non-latent model, with just boxes, where you have like 0 degrees of freedom, if you want to sort of artificially create degrees of freedom, you could get rid of those covariances. And as long as you still have good model fit, you're still specifying the model validly. And so it is okay to leave those out in order to increase your degrees. But if you can't achieve good model fit and because you've deleted covariances, then your model's no longer valid. Okay, on chat, there's more. Good catch. Connect com to decision quality. Whoops. Compuse to decision. Oh, thank you. Good catch. Haven't connected compuse to decision quality. And usefulness to information acquisition. There we go. Good catch. Last one here. Can control variable be latent variable as well? Yes. So social desirability is latent. Everything to everything. Yes. Atheoretical. Sorry, Isaac. We're totally atheoretical today. Okay. Okay. I'm going to save this and run it and hope it doesn't explode. Another reason you'd want to use a non-latent model instead of a latent model is if you had low sample size. So a complex model like this with all these degrees of freedom because of all the parameters requires a fairly high sample size to run in order to run validly, in order to minimize into a usable solution. Whereas a model like this, yes, save. A model like this requires very low sample size to run. I could run this with a sample size of 60. It'd be fine. Probably 45 even. So latent, well, at least these are non-latent here. These are just one variable that has a number associated with it. There's an actual number that goes behind playful, or 379 numbers, because we have the n of 379. In the latent model, yeah, but it has real numbers behind it. Whereas anxiety here, it has no real number behind it because it's not being measured directly. Yeah, so this is latent because it's hidden, there's no real measure. It's being measured indirectly by these guys that have real measures. Yeah, latent means, yeah, you can't directly observe it. Okay. Okay. Repeat the sample size for non-latent model, please. Oh yeah, I mean, that's not a critical point, but there, for example, with experience here, it has a real number behind it. It has 379 numbers behind it because we have a sample size of 379. So for experience, we have 379 people who gave us a response for the experience item on our survey. There's an actual number that they gave us. So that's where the numbers come from. Whereas nobody gave us an actual number for anxiety. They gave us numbers for all these anxiety items. And then we sort of infer a value for anxiety out of those items. Yeah, no, the other way around. Endogenous trumps exogenous. Really, if you don't want to use those terms, it's cool because it's like type 1 and type 2 errors. Nobody can ever really get them straight. Yeah. And false positives versus false negatives. Like I know what they are now because I have to say it all the time, but type 1 and type 2, I still get mixed up. Yeah. Also like ontology and epistemology. What does that mean? I don't know. Overall, the observed variables, we have 379 responses. Yeah, we can mix it up. We can have observed variables and latent variables in here. It's called a hybrid causal model. Yeah, because it has both. Oh, the whole model's hybrid, this one. No, it's not latent or non-latent. It's hybrid because it has both. Again, not super important point on how you label it. If I have a small sample size, which size should it be in such a way that I can use SEM, but with non-latent model? As I mentioned yesterday, there are so many different calculations for sample size. And the reason is because it really depends on the consistency of the responses. More error means you need more sample size because sample size forgives error. It reduces error. But if you have really consistent responses, meaning you have very low error, you could run it with a sample size that's really low. So it really just depends on error. A good rule of thumb for Amos is about 5 times the number of boxes you have, with a minimum of 50 sample size, not 50 boxes. Good point. Check this out. This is an interesting observation. Each latent variable has an anchor, a constraint somewhere. Notice our observed variables do not. They do not need them because they're not being indirectly measured. But there's no anchor needed. There's an actual number. No anchoring needed. There is one. There was. Where'd it go? Where'd it go? There was. Maybe it disappeared. I better fix that. Good catch. Social desirability needs an anchor somewhere. So we'll just put it on the first one. Very good catch. Better save that. All right. Quite a bit of dialogue here. If our DV is a number, would it matter for Amos? Oh yeah, could you have a dependent variable that's observed rather than latent? Definitely. Firm performance, revenue, share price, those are all really good dependent variables. Or score on an exam, things like that. Yep. Error rates, a little bit there. Oh wait, sound faded a little bit there. I believe he was asking about the sample size for the non-latent model. You said something about 60 or 45. Oh, sorry, yeah. Sample size, it depends on a lot of stuff, but a minimum of 50 and at least 5 times the number of boxes you have, or 50, whichever is more. Similar to DV as a number. DV as a one observed variable would work with SEM? Yes. Doesn't work very well when it's a binary value, like yes or no, true or false. But it works fine if there's some variance in it, like income or revenue or grade on exams or error rates in manufacturing. Those are all just single observed numbers. They can work as the dependent variable. Okay, I'm going to run this model before there are any more questions. But before I do, go to the analysis properties here, this colored abacus. And we want to check the box for a few things. We want to uncheck residual moments if that's checked. I want to check modification indices. Keep it at 40. And I definitely want to check squared multiple correlations. This is your R squared. It's how much we're actually able to predict. I want to go back to estimation tab. Make sure this estimate means and intercepts is not checked. Okay, with that in mind, we're going to run this model after we save it. Here we go. Huh? No Bootstrap. Not yet. We don't need to. I'm just looking at it for now. Bootstrap is required if you're doing mediation. It's also required if you're estimating a user-defined estiman, which we'll do later. It's like a user. It's a custom variable, custom measure. I'll show you in a bit. Okay. So we ran it. It ran. Hooray! We have degrees of freedom of 530. You can see down here. So we have quite a few degrees of freedom. We want to check a few things. First, we want to check, do the numbers look rational? So hit the up arrow, go to standardized estimates, look at your model. First thing I want to show you is these R squares. 40% R square in information acquisition, 33% R square on decision quality. Those are great numbers. In social sciences, typically an R square over 30 is good. Anything over 40 is just great. Different sciences, different numbers. Compuse 22 R square. Usefulness is at a 13, I think, R square, so not fabulous. You can see the amplitude of the effect. So these are regression weights here. It's the coefficient in the regression equation. Slope. 47 is great. Anything again above like 0.2 is pretty decent. So predicting information acquisition very well with usefulness, and also we're predicting decision quality really well with usefulness. Does anything else predict them is the question. We go put our mouse cursor over these lines. We don't care from social desirability. We want to see from playfulness. 0.1, meh. 0.25, pretty good. 0.04, meh. 0.04, meh. Comp use is kind of useless as a predictor. That's unfortunate. But playfulness predicts comp use really well, a 0.4. Pretty nice. Okay, so we're just sort of feeling out the model a bit. Yeah. R square, 0.33. So that's the actual amount of variance that is explained by all the predictor variables. So we can explain 33% of decision quality with these variables. If we were running a financial model and this thing over here was revenue, and we were predicting 33% of revenue variance, this would be, we could publish something in Science. They'd even take it. Because if you can predict revenue with 33% of revenue, you just made a powerful model. Typically in finance, you're looking closer to like 4% or 2%, or even less sometimes. Okay.
So having said that, that includes the the mediator variables as well, correct?
Correct. Anything that has a line going into decision quality is predicting.
That causal path, right?
Yeah, and causes that R square.
Yeah.
If your model did not run, it could be due to several amazing things. Did you get an error? Oh, that's unfortunate. I'll have to look at it later. I'll save this one so you can pick it up. Okay, and it's saved. Okay, let's go to the chat window. What did we check again for R squared? Didn't get those. Can you analyze these numbers before addressing model fit? Fabulous question. Do these numbers mean anything before we address model fit? The answer is no, not really, because we don't know if this is a valid model. So we should really check model fit. Let me show you R square again, how to get that. Click on the colored abacus right here. And in the output tab, check the box for squared multiple correlations. That's your R square right there. Let's go look at the output and see if we even have model fit. Oh, I wonder if we can use the plugin. Let's try that. I've never tried a plugin for model fit on a causal model. I'll break. It worked. What's Magic Clean? Magic Clean is a plugin one of my research assistants wrote, and what it does is it fits the whole model onto the canvas and then makes all of the arrows symmetric and clean. I'll show you half of it. Essentially, it does this. It selects the whole model and then uses the magic wand to realign all of the arrows. But it also shrinks it down onto the canvas. Okay, back to model fit. It worked. We actually have tolerable model fit. The only one that is in the acceptable range rather than excellent range is the CFI, but 0.946, there's nothing wrong with a 0.946 in CFI. So I'm gonna say we're great. Don't need to change a thing. Cool. So that means what does that mean? That means the model is valid. It means that any relationships we do observe, all those R squares, all the regression weights, they're valid. We can have confidence that they are accurately representing the reality we captured with our survey. Okay. If we didn't have good model fit at this point, we do what we did before. We go look at modification indices and see what it recommends. My guess is it's going to recommend nothing unless we lower that threshold. And then the first thing it'll recommend is we covary useful and compuse error terms, these mediators error terms. Excuse me. Okay. The next thing we can do, actually, I'm going to talk in the slides for a sec. Not these slides. Where'd you go? Here you go. These slides. So we did this. Let's talk about this real quick. There's this thing called multicollinearity. Multicollinearity, anytime you're predicting something with multiple variables, you have the potential for what's called multicollinearity. That is the part of the dependent variable you're predicting is being predicted by multiple variables. How to say this properly? When you're predicting a dependent variable, you don't predict all of its movement. You predict certain portions of its movement, of its variance. And the question is, do my independent variables that are doing the predicting predict different portions of that variance or the same portion of that variance? If they're predicting the same thing, they're redundant and I don't need them all. And it might be inflating my R square. So in this example, IV1 is predicting it, IV3 is predicting it, but is IV2 even useful? It's predicting a little bit of unique variance, but not much. How can we assess that? We actually can't do it in Amos, unfortunately. What we can do is use those factor scores we created earlier to do it in SPSS. So if you open SPSS, and I better slow down here to let people open it. Open SPSS, we're going to do a regression and assess multicollinearity. And do you have to do multicollinearity assessment? The answer is yes. Because you don't know if that R square is being artificially inflated by multicollinearity. Okay. You'd go to Analyze. Analyze, regression, linear, just like before. But this time, what you're going to do is you're going to throw your dependent variable in that dependent list. Our dependent variable, using factor scores here, let's start with decision quality, down at the very bottom. So decision quality is my dependent. In my independent, I'm going to use all the factor scores for all of my independent variables, compuse, and mediators. Compuse, playfulness, anxiety, usefulness. Whoop. Yeah, so in the model, in the model over here, we have anxiety, playful, compuse, and useful, all predicting decision quality. So we want to see if there's any multicollinearity issues. Yes, we're going to use those 4 factors there. We could also add experience, age, and social desirability if we really wanted to. It's not going to make a huge difference. Let's go ahead and do that. Correct. Regardless of the significance of the regression, we're going to put them all in to see if they have multicollinearity issues, overlapping explained variance. I'm going to throw in age and experience just for the heck of it, because we are using them to predict. What you want to check is in the statistics box here, you want collinearity diagnostics. Right there. and continue, and run. It runs, and this is the table we want to look at right here, the coefficients table. And it's the VIF column we're interested in. Hello? Somebody's talking on that side? Okay. We're going to look at the VIFs here, variable inflation factor. Anything greater than 3 is considered potentially a multicollinear. Anything greater than 5, you're running into trouble. Anything greater than 10, red flags, very bad, very bad. In fact, if you have a 10 here, you might consider deleting that variable entirely because it's completely redundant. It is not adding value. But these are all 1s, so we have no multicollinearity issues whatsoever. Again, if we're over 3, I would note it. If we're over 5, I decide whether I want to delete it or not. Probably I wouldn't because it's part of my theory and it's hard to delete your theory. If we're over 10, I have very little choice. My hands are bound. I should probably delete that variable. No, multicollinearity cannot be determined by looking at the regression weights alone. You have to do a regression with the VIF calculated, and that's the true indicator. Notice we had a really high regression from usefulness to decision quality. It was like 0.5 or something really good, but no problems with multicollinearity. Yeah. If we had a VIF, or it would be over here. If we had a VIF here, it was like 10. Let's say it was, let's say usefulness had a 10 on it. Highly multicollinear. What that means is usefulness is not explaining any unique variance. Its variance is explained by these other variables. So usefulness is out of the family. Yeah, so we're going to test one DV at a time. We're going to do the other one right now. So we did decision quality. We're going to do information acquisition now. So you can't do it at the beginning with the cleaning because you don't have these factor scores yet. Yeah, you can only do this after you get factor scores. So I swapped out decision quality for information acquisition. Run it one more time. Correct, we got these factor scores from Amos. You can get factor scores from an EFA. So you could do this way early on if you want, but our EFA and our final CFA are so different that I would wait. Okay, notice all 1s, again, no problem. We have no multicollinearity issues. What would you report in your manuscript? You would say we ran, because we have multiple variables predicting our dependent variables, we ran a multicollinearity test, and all VIFs were less than 2. So we have no multicollinearity issues. A reference for multicollinearity, just use Hare, 2010. Okay. Here we go. So that's VIFs.
So you'd run the test regardless, correct? I mean, nothing on the structural model would give you an indication, so you would just go ahead and run it since you've got multiple dependent variables and numerous predictor variables. You just want to make sure that you have no multicollinearity, correct?
Correct. Anytime you have multiple independent variables, you would need to run a multicollinearity test.
Okay, thanks.
If you only had one independent variable and multiple dependent variables, and I've seen models like that before, there's no, multicollinearity is irrelevant because there's only one predictor. Mahalanobis? And me neither. So there's the Mahalanobis distance, which is calculated in Amos. And what that is it's not multicollinearity, but it is a multivariate outlier. And I hate it with a passion because what is a multivariate outlier? A multivariate outlier is someone who doesn't match your theory. But can you throw someone out of your sample just because they don't match your theory? You can't. And so, but people will do it. They'll go look at the Mahalanobis D, the distance. They'll find those who violate the threshold. And then they'll say, these guys don't match my theory. They're outliers. Therefore, I'll kick them out. But what are you doing when you do that? You're doing self-fulfilled prophecy. Yeah, this is my theory, and I can prove it because I've kicked out everyone who doesn't agree. Governments like that too. Nope, not even. Gospel according to St. James. Not St. James, just James. Yeah. Slip of tongue. Yeah, there are cutoffs published on Mahalanobis D. I think it's 0.001. It's super strict. Correct. The reason we're doing multicollinearity is to ensure that each independent variable is adding unique value in predicting the dependent variable. It is sufficiently unique. Yeah, exactly. So inevitably they will all have some overlapping predicted variance. That's why we have the adjusted R-square in a lot of multiple regression programs. Yep. So that being able, having the survey respondents being able to distinguish the independent variables, that's actually a separate issue of discriminant validity. This feels the same, but it's slightly different. Yeah, we'd have to have already passed discriminant validity and then come here. Yep. Yeah. Yes. Okay, so R-square is all, let's use this right here, this guy right here. Let's say the R-square is 40%. That is all of the variance additive of every variable explaining that dependent variable. So it's all of IV1 explaining all of IV2, even the overlap, all of IV3, even the overlap. Adjusted R-square is when you remove those overlaps. There's actually another R-square called something else, where you exclude any overlap, period. No overlap counts at all. It's a really strict R-square. Yeah, adjusted R-square will always be lower than R-square. Yeah, it should be. Should be, but Amos doesn't report it. And in order to get it, you have to. Problem is, you can't have latent factors in SPSS. You can't do a model in SPSS like that. And so each one has their limitations. So we use Amos, but we'll use R-square. And the way we say the R-square is valid is by saying, look, there's no VIF issue. There's no multicollinearity. And so the R-square is a meaningful number. Yeah. Mm-hmm. So discriminant validity is essentially saying we have this cluster of correlated items over here. We have this cluster of correlated items over here. Are they separate clusters or are they the same? That's discriminant validity. Multicollinearity is how does this cluster of items and this cluster of items predict some other cluster of items? Yeah. So one's about the closeness of the clusters. The other is about the predictability. Yeah, or predictiveness is the right word. Okay. Nuances. Yeah, this is another preparatory thing. We have not tested any theory yet. So much buildup. And we're not even ready yet. We still need to do multivariate outliers, which we won't do with, actually it's not multivariate outliers, it's multivariate influentials. We'll do that with Cook's distance. What this is it's saying in any given relationship between two variables or multiple variables, you have the potential for someone who is so counter to your theory to skew the rest of the respondents. You could have one person being an oddball that'll take that regression of 0.2 and pull it down to a 0.18. And are we allowed to kick them out? Possibly, in as much as they are breaking the majority of respondents' relationships we're observing. Yeah, we have some justification. Now, if we start kicking out 20, 30 people, or more than a couple %, then you're starting to bias things really bad. You don't want to kick out a lot of people, but you want to see, is there someone who's a real oddball? So let's go look at that. In SPSS, if you were to go to Analyze, Linear Regression again, so regression, linear, just like before. Someone is not muted. Let's see. It's KIS. Okay. There we go. Okay. What we want to do is we can assess these one at a time, or we can assess them all simultaneously. However you prefer. The more rigorous way would be to do it one at a time, one independent variable at a time. So we'll get rid of all these just as an example, except playfulness. Okay. Between playfulness and information acquisition, is there an oddball? Let's find out. Go to Save and check the box for Cook's distance. Hey, look, there's Mahalanobis. Here's Cook's distance. Save that. What that's going to do is it's going to create a new variable for their oddity, their difference between everyone else. It's sort of a, I'll show you. I'll just show you. If we go to Graphs Chart Builder, and we throw in a scatter dot. So you click on scatter dot, and you click and drag the one you want up into there. And then you get to the very bottom, you see we have a new variable called COO1. That's Cook's distance 1. This is the influence of a single respondent on that relationship we just tested. So if I drag that into the y-axis, I can do anything I want for the x-axis, but I'll throw information acquisition in there because that was our DB. But you could literally stick anything there. It wouldn't matter that much. ID is something people use fairly often. You hit OK, it's going to create a graph. And hey, it looks like a smiley face. Cool. That's fun. What this graph is showing is their influence, each respondent's influence on that relationship. You can see most people are normal. They're part of they go with a typical relationship between those two variables. Whereas these two guys are kind of oddballs. How odd are they? Not odd. The cutoff is 1.0. This is 0.15. So these guys are not odd. They're odd for this group, but not so odd that they're pulling the regression line away from its true path. If it was above 1, I would say these guys are pulling the regression line away from its true path. I have justification for removing them. Oh, I'd say we looked at, yeah. Yeah, a set of responses, yeah. So for each respondent. So let me say it, let me sort of summarize it for the remote folks who can't hear your side of the conversation. So the way you'd write this up is you'd say, we looked at multivariate normality, and we did it through a Cook's distance analysis and found that in no cases did a respondent exhibit greater than 1 for Cook's distance, meaning that none of our respondents were influential outliers from a multivariate perspective. For those who didn't catch all that verbiage, it's now recorded. Okay. Yeah. Yeah, if I had found someone that was over 1, over that threshold, I would be pretty inclined to go and delete that person. Reason being, we have this fairly consistent, you can see fairly consistent pattern of responses here. And so the relationship is probably pretty consistent, except this one person is pulling that relationship from a nice consistent line to a flatter line. No, no, no. We would not go back and rerun the CFA and the EFA. It's one person. So this is very different. So this brings up the issue of measurement versus structure. So that one person did not mess up our measurement. It messed up our structure, our causal relationships. So our measures are still valid. It's the relationship between those measures that this person was messing up. So this person didn't mess up any of our measures at all. We can kick them out and still be fine. Yep. Yeah, we delete that guy from the .sav file, and then we go back to Amos, relink the new file, and carry on. Exactly. The way I measured your satisfaction is valid, whether you were satisfied or not. One good example of Cook's distance being high. Let's use this satisfaction with the bootcamp. Let's say we have 2 variables. One is your engagement level as participants of this bootcamp. That's the predictor, that's the IV. The dependent variable is your satisfaction with the bootcamp. Let's say all of you worked hard and were satisfied, or worked little and were not satisfied. Very consistent, right? Relationship. But one of you worked your tail off and was miserable. You had sort of, everybody else was either work hard and satisfied or work not hard and not satisfied, very consistent, but you didn't follow that pattern. Your Cook's distance would be way up there. And you're pulling that consistent relationship out of whack. So we delete you. You wouldn't get a certificate. Okay, just kidding. We are. And this gets to quantitative versus qualitative rigor and richness. In a quantitative world, I'm cool with that. Because what we're trying to do quantitatively is be universally generalizable. Qualitatively, I would be fascinated to go and have an interview with that person who worked so hard and was so unsatisfied. Because that's the person that's going to help me make this an even better bootcamp. So from a practical standpoint and a qualitative research standpoint, that's the interesting person. Everybody else is just Joe Schmo. But that one person who broke the mold, that's the interesting person. Please do. Yeah, we're removing someone who's breaking our generalizations. Because it's only 1 out of 379, we're still representing reality as best as we can. It's that person who has more influence than any of the rest of you. That's the thing, that's the problem. This one person who's different has more sway on the regression line than any of you. Yeah. So it's not that we're failing to capture reality in this case. We're actually bringing it back to more real. Again, general speech. But qualitatively, that's the most interesting person. Oh, yeah. Yeah, you may want to do that. So what do you report when you find someone like that? You say, we found someone who's pulling the regression away from its true line, looking at the Cook's distance. We made a point to follow up with that respondent, if that's an option, if you tracked them at all. Yeah. How so? Oh, I wouldn't. I would just say they were an influential outlier. You may say, for example, here's the consistent relationship, but here was their relationship. Okay. Okay. We did model fit. We looked at multivariate outliers. We looked at multicollinearity. And now it's time for a quick break. And then we're going to get to mediation and moderation. Excellent. I'm actually going to answer these questions on chat first. How do we get factor scores again? Never mind. Could you please theory behind Cook's distance? We did. Threshold is 1 or 1.5? 1. And notice those are decimals. Maybe you just can't see it because it's small. If I zoom in here, it's not 1, it's actually 0.1. So nobody's beyond the 1 threshold. As soon as you get model fit, you leave the model like it is, or can you improve it by deleting non-significant paths and adding correlations? If we have good fit, we don't need to go any further. The model's valid. We don't need optimal fit. We just need good enough fit. So we're not going to add correlations or delete any paths right now. Cool. All right, 5-minute break. Yeah, here I come. I'm going to pause this, make sure I start recording again. Recording. There are 2 questions over the break that I want to address. One is here, and it's related to the other one. Someone says, nevertheless, removing insignificant paths should improve model fit, right? The answer is, yeah, it'll improve model fit of the parsimony-related measures. We're actually missing a few people. We'll wait. Okay. Well, yeah, we'll wait. Okay. Sorry I didn't look up before I started again. I'm in my own little world. Always have been. All right. Here they come. Okay. Here we go. So there were 2 questions of the break. One was about removing non-significant paths, its effect on model fit. So there are 3 different types of measures of model fit. One of them, though, is called a parsimony-adjusted measure of model fit, like the RMSEA. And another one that's not coming to mind. RMR, maybe, the SRMR, could be. Those take into account how many parameters you're accounting for, and the fewer parameters you account for, so essentially the higher the degrees of freedom, the better those measures. So yeah, if you delete a path that is not significant, you're freeing up a degree of freedom. You're creating a degree of freedom, I guess. And so those fit measures will improve. But your chi-square will go up at the same time. Because as soon as you don't account for a measure, or a parameter, that increases the distance between the observed and proposed covariance matrices. So the chi-square will increase. So there's a trade-off. A related question. What if you have a control variable that has no effect? So let's look at that real quick. Let's see if we have a control variable that has no effect. Look at this over here. Experience to usefulness, 0.02. You think that's significant? Probably not. That's a regression weight there. And anything less than 0.1 is probably never going to be significant unless you have tons of sample size. So can we delete this arrow, free up a degree of freedom? Yeah, we could. Actually, there are different schools of thought on it. Some say, yeah, if you have what's called an impotent control variable, you can delete it entirely if it has no effects. Let's see. Here's a 0.00. Here's a 0.03. And here's a 0.17. That probably has an effect right there. So we couldn't delete experience entirely, but we could delete these 3 paths. Do we need to? Not in a latent model like this. because we have tons of degrees of freedom. So we have the flexibility to just keep it. If we had the other model, if we had a non-latent model, let's actually go to one right now just to sort of put this in a firm model we can look at. If, for example, frequency here had no real effect on usefulness, I would be very interested in deleting that path because it is reserving a degree of freedom. I need as many as I can get in one of these non-latent models. So I would delete as many as I could. Now, if I delete frequency entirely, my potential body of degrees of freedom drops because now frequency doesn't exist and all of the arrows that could have been related to frequency are no longer even part of this model. And so the potential maximum number of degrees of freedom has dropped. So bear that in mind. Okay. And on chat, somebody says, are the CRs useful to know when paths are significant or not? Let me show you. Let's go over to here. We've seen CR before, but the one in Amos is different. We calculated CR when we looked at the AVE in convergent validity. CR stood for composite reliability. The CR here in this column is not composite reliability. CR stands for critical ratio here. This is like a T value or a Z or an F value. And they're an indication of the amplitude of the effect. And it's by dividing the CR by the SE, standard error, that you get the p-value. Maybe it's the other way around, SE by the CR. I can't remember, it's one of the two. It's some ratio in there, and you get a p-value. So yeah, CR, the bigger the CR on an absolute scale, the greater the significance. So we can see this one, 0.249, not significant. 1.571, pretty close to significant. 9.59, definitely significant. Typically, a critical ratio above the absolute value of 1.96 is significant at the 0.05 level, two-tailed. 1.96. Okay, but you could just look at the p-value as well. Learned something today. Critical ratio. Yes, critical ratio. Okay. The next thing to do, we've addressed model fit. It is a valid model, the way it is specified currently. The next thing we need to do is test our hypotheses. Oh, I was going to write to next break. I need to remember to put together a quick exercise for you on hypotheses. Remind me. Okay. But let's do some mediation. Mediation is tricky. Mediation is really tricky. Conceptually, just real quick, conceptually, I know most of you probably have this down pat. I'm going to quickly review mediation conceptually. So when we tested it, it makes sense. People mix up mediation and moderation all the time. Mediation is the reason the independent variable has an effect on the dependent variable. In this case, curiosity and learning. We're saying that curiosity leads to learning, but only because curiosity leads to discovery, which leads to learning. Discovery is the real reason curiosity affects learning. Now we could remodel this and say that curiosity leads to learning, but only in the context of people who are discovery-oriented. Anyone who is not discovery-oriented, their curiosity is stifled at some point, it's stopped, and it doesn't lead to learning. I think it works better as a mediator in this case. So moderation is about context. Mediation is about process. Mediation is the reason for the effect. Moderation is the under what context does the effect take place. Which I just sort of talked about. Here's another one. Interest leads to learning, in as much as interest leads to engagement, which then leads to learning. How do you do it? We're going to do this right now. In a model like this, there's a trick. Unfortunately, Amos does not allow you, by default to assess individual mediated paths. What it does, let's just do it, and that'll make sense. I'm not talking abstractly. Go here. Go to the analysis properties, and then go to the output tab. Check the box for indirect, direct, and total effects. A mediation is just an indirect effect. That's what we call it, an indirect effect. Whenever you're doing indirect effects, you also need to bootstrap. So go to the Bootstrap tab. I love saying bootstrap. And let's add a 0. So we're doing 2,000 bootstraps. What is bootstrapping, you might ask? Also check this box here for bias corrected. And we'll set it at 95. You can leave it at 90. It doesn't matter that much. It depends on how confident you want to be. Okay, what is bootstrapping? Bootstrapping is you take the sample, you run the model, except instead of having respondent number 17, that respondent's values, you replace all of that respondent's values with the average values for the rest of the sample. And you do that a bunch of times. In fact, in this case, we're going to do it 2,000 times. And you see if the analysis is robust to that bootstrapping. What that also does is it reduces error and gives you more accurate estimates for regression weights, for R-square, for everything. It also allows you to calculate an indirect effect. So we are going to bootstrap. I'm going to save this as mediation, file save as. Causal, it's a hybrid actually, hybrid, mediation. And run it. When we run it, it's going to take a little bit longer than usual because it's running 2,000 times. Give it a sec. While it's going, I'll answer chat. Can you explain that again? Sure, definitely can. The process behind bootstrapping. You can't see my hands over there, so it didn't make a lot of sense. I use my hands a lot when I talk. So bootstrapping essentially says, let me grab the data here and it'll make more sense. Here's our data set. When you run a bootstrap, you take these every 7th record or something like that. And instead of using the values in that record, you replace all of those values with the mean for the column. And so instead of a 2 here, maybe it'll be a 2.27. Instead of a 4 here, maybe it's a 2.8. And you run the model, you estimate the model using those replaced values. And then you do that selecting different ones next time. And again, you do different ones the next time. And you do this 2,000 times so that when you're done, you have pretty robust and reliable estimates that it's produced. Because you've tried it with different sampling, is what it is. And you've done it 2,000 times. So what it does, it then takes roughly the average of the 2,000 estimates and reports that as the bootstrapped estimate, the bootstrapped mean. Okay, that's all random. To some extent, it's random. If I were to show you over here, there's a random number. Wow, that's stupid. My random number is 1. That's not very random. You could use an original random generator. That would work probably better. But it starts with, 1 is a terrible number. Yeah, change that. It's just a C. So it starts with the first record, and then it throws randomness from there. You can start with 17th record or 99th record, and then it just loops through it. So 1, I guess, isn't that terrible. It just always starts with the same one. Okay. It's replacing records with averages. And then it'll rerun it. It'll put the numbers back, and then choose different records and replace those with averages. And then run it, and then put them back, and then run it again. And then it takes the average regression weights, the average R-squares, the average standard errors, and reports those. It does have a smoothing effect. You don't have you don't have extreme values. You actually notice when you bootstrap, the p-values are typically sedated a little bit. Yeah, you don't get these extreme p-values. You get very rational p-values. Smooth things out. Yeah. Yep. Can you please show what you have chosen for bootstrapping for Amos? Yes. Again, go to the output, go to the Bootstrap tab here. Bootstrap tab. Check perform bootstrap. I did it at 2,000 times. With the power of computers these days, anything less than 1,000 is unreasonable. Don't do anything less than 1,000. And then I did bias corrected confidence intervals. Okay. And I have to run it again because I clicked on something. Darn. Why do we need to do this for mediation? So in order to calculate indirect effects, confidence intervals, you have to do multiple sampling. It can't be run on a single. It's more smooth. It's more accurate when you run it on a bootstrap. Rely on it more. If you bootstrap with 4 records versus 1, the results would be different or similar. The results will actually be different every time you run it with a bootstrap because there's some randomness in it, but they'll be fairly similar. Okay, let's go look at the output. Mine's hiding back here. There we go. So if we go to estimates, you'll see there's a new, we had scalars before, right? But now there's also matrices. If you open up matrices, you'll see we have total effects, standardized total effects, direct effects, indirect effects, standardized indirect effects. I'm going to click on the standardized indirect effects. And zoom out a little bit. Standardized indirect effects. And these are those standardized effects. Estimates. Notice I have estimates selected down in the bootstrap area. So these are the mean of the 2,000 estimates, and they're standardized. If I go to confidence down here, you get the bias corrected percentile method. Then we'll also see the p-values for standardized indirect effects. Let me go down. Let's pick a specific one. Why is it showing all of them? Oh well. Let's pick one specifically. So let's say we were theorizing that anxiety had, that's a terrible one, playfulness has an indirect effect on information acquisition through comprehensive use. So this path right here, playful to comp use to info acquisition. I could go look at this table and go look at playful right here. See, this is the standardized indirect effects, lower bounds. I don't want the lower bounds. I want the significance here. Here's the significance. Playfulness to information acquisition is right here. This, nope, I need it to the actual, this one. Okay, you see here's information acquisition, the higher level latent variable. And the p-value for that indirect effect from playfulness to information acquisition is 0.001. Here we go. So this is the indirect effect from information acquisition, or from playfulness, excuse me, to information acquisition through every possible indirect path. And in this case, that's from playful to comp use, information acquisition. That's playful to usefulness to information acquisition. So it's actually reporting both together. Amos does not have the capability to separate those unless you do something called a user-defined estimand, calculate it yourself. So if you were to theorize about this, using this approach, you could not theorize that comprehensive use mediates the effect of playfulness on information acquisition, because you can't test it. You'd have to theorize that the effect from playfulness to information acquisition is mediated by comp use and usefulness. That would be your theory, you would argue. And then that would be the theory you test. But we can separate it, so let's separate it. Okay. What you need to do is you need to set a user-defined estimand, which I've written for you. You're welcome, because it's programming. I thought you wouldn't want to do that. Down in the bottom left, there's something called, there's this little label, not estimating any estimand. Estimand. Yeah. Let's estimate one. So click on that, select estimand. Where is that estimand? It's in the estimands and plugins folder. You just point to it directly, or if you've downloaded it into your downloads folder, go find it there. And these estimands are available in the Google Drive folder that is being shared. The one you want is My Indirect Effects, this one. And just hit open. When you do, magically nothing happens. Except this change is down here, estimating my indirect effects. No longer says not estimating, it's now estimating something. To run an estimand, you have to bootstrap. You can't run an estimand without bootstrapping. So we've already got that covered. This estimand also assumes that you have named two paths, two parts of your indirect effect. So let's take the playfulness to information acquisition route. I'm going to name playfulness to compuse A, capital A, because that's what it's expecting. Zoom in here. It's expecting one path to be called A, one path to be called B. And it's going to multiply those, create confidence intervals around it, and a p-value. And then this second part of the path, this one right here, I'm going to name B, capital B. So it's going to, the estimand is going to multiply A times B 2,000 times with this, with the replacing in the bootstrapping, and it's going to use that to come up with confidence intervals and a p-value for this indirect effect. Just this indirect effect, not all of the indirect effects simultaneously. So we run that. It runs eventually. Still running. There we go. It has run. Go look at the output, and there will be a new thingy. Let's see, in estimates, scalars, user-defined estimands. That's new. Click on that, and let's expand it by clicking on, at the very bottom here, bootstrap confidence. What that'll do is it'll expand it a little bit and give you everything you need. So the estimate, the indirect effect for that relationship is 0.013, very low. And there is no significant p-value for that. So that, even though we found in the last test that there was an indirect effect that was significant, turns out this particular indirect effect is not significant. Do you have a question? Yeah. Ooh. The question was, is that estimate standardized? I don't think it is. I can double check though. Here we go. I can go here and edit my indirect effects. Don't you do this. Don't edit the, unless you're a programmer. And I believe it is unstandardized. Okay. Cool. It is unstandardized. How would we get the standardized version? I don't know. Yeah. But let's say we wanted to test the other. Let's try the other path. Playful to information acquisition. Through usefulness? Yes, through usefulness. What we do is we get rid of the A here by double-clicking it, delete, get rid of the B, delete, and we'd move it over to this path. Call this A, and then from usefulness to information acquisition, call this B. So now we're testing that indirect effect, A and B. Run it again. And we'd hope this one's significant, since together they were significant. There was a question on chat. Looks like only unstandardized paths have p-values in Amos. Good observation. Let me show you something. If you go to the output, go to the estimates. Notice in regression weights, this is unstandardized. These have p-values. But if you go down to the standardized regression weights, no p-values. But those p-values for unstandardized are relevant to the standardized. It's the same path. Okay, let's go to estimates, scalars, user-defined estimands, bootstrap confidence, like before, and we have significant mediation, only through usefulness, not through comp use. So had we theorized there was a significant indirect effect through our mediators, we wouldn't have known which one it was through unless we had done this and separated it out. Cool. P-value is significant.
Couldn't you also test it in SPSS as well, though?
In SPSS, using the process plugin by Hayes, right? Or is that not what you're talking about?
Yes.
Yes, using that. Yes, you can do this in SPSS. The problem is in SPSS, using process, you cannot use latent factors. You'd have to use observed variables.
Okay, thanks.
You're welcome. This one, yeah. Oh, yeah, if you guys don't see this bias corrected percentile method, it's because you're missing it here. If you go to, oops, if you go to the colored abacus, go to the Bootstrap menu, and check the box for bias corrected confidence intervals. You're welcome. I want to say a word on confidence intervals. Oh, it's going to make me rerun it. No, here it is. Yes. Okay. You may know this because you took Stats 101, but when I took Stats 121, it didn't make any sense to me and only clicked like a few years ago. That's how slow I am. This lower and upper bound doesn't contain 0, which is why this p-value is significant. If this lower and upper bound contains 0, it would be much less likely that that p-value was significant. Because this lower and upper bound are the lower potential and upper potential for this estimate. If the estimate is 0, the null hypothesis is supported, that there is no effect. Therefore, the p-value would be not significant. Yeah, from 0.078 moving all the way up to 0.192, 0 does not fall in that range. But if this was a negative 0.078, 0 does fall in that range. Excuse me. That never made sense to me until like a couple years ago, which I know some of you are laughing on the inside really hard. It's okay, you can laugh. I'm going to blame my teacher too. Yep. Oh, I definitely blame, yeah, I'm sure he said exactly what I said. And I was not listening, I was dating. Anyway, why? You know what I'm saying? My brain wasn't on stats, not these kind of stats. Okay, how do you load an estimand into Amos? I'll show you in just a sec. Interesting and surprising, given how output is formatted. I think, thank you. How would you compare direct and indirect effects since indirect are not standardized? Oh. Well, what you could do, I'm going to throw out some stuff here that we haven't been doing. So the best way to run everything we've been doing up to this point is to actually, after you've done all your data cleaning in SPSS, standardize everything. Standardize all the variables. And then move forward just looking at unstandardized estimates, because those unstandardized estimates are now on a standardized scale, and they're all comparable. So in this case, the unstandardized indirect effect would be the same as the standardized indirect effect. So, but doing it the way we've done it, can you compare them? The answer is no, not really. So, many apologies. Only if you standardize all the variables first. Okay. Yeah, the question for those who can't hear, would you standardize just the perceptual Likert scale variables, or would you standardize everything? The answer is everything, so they're on the same scale. No, you wouldn't standardize nominal variables. Yeah, not categorical variables. So that's the most appropriate way, according to the most recent literature. But I don't teach that because it adds one more layer of complexity, and it doesn't follow any of the videos I've created, which I know people rely on. And so I'd have to redo all the videos, which I'll do next year. Yeah. It does. Yeah. So M+ is a great program. Same with Stata, really good. We don't teach Stata or M+ in most undergraduate or executive courses because hard enough to get you to use a graphical user interface, getting you to program it, because M+ requires some syntax and programming. Same with Stata. It would be very difficult for some, not for everybody, but for some. Okay, more on chat. Looking through your references and did not see a reference on mediation that is related to your recommendation. So the approach I'm taking is it's just using bootstrapping to generate confidence intervals. So you can cite literally like any of those mediation references over here. What is this? So F mediation. There it is, mediation in 3.1. Any of the more recent papers, McKinnon in particular, would support what I'm doing. So would Preacher. They preach a bootstrapped indirect effect. So none of them will use the words user-defined estimand because guaranteed none of these guys use Amos because they're too sophisticated for Amos. They use something where you can actually program it in. But that's essentially I'm bringing programming into Amos by using an estimand. So you can use either of these, McKinnon or Preacher. Yeah. Yeah, the plugins I wrote were in VB.net. Or C#. Yeah. Okay. There was one more here, one more chat. First, at what step? What is you use the same scale across all variables? Oh, what do you mean? Yeah. I said using the same scale across all variables. When you standardize all the variables, then it doesn't matter what scale they were on before. They're now all on the same scale. Standardizing, what it does is it makes the mean 0 and the standard deviation 1 for all variables. So they're all on the same scale. Okay, but it doesn't end up with 0 to 1. It just means the standard deviation is 1. So it can still end up with larger values, but same scale. Okay, that's mediation. Like I said before, you have all this buildup, and then you test mediation. Actually, testing mediation took us a few seconds, a few minutes, and we can determine whether we have a supported hypothesis. Everything else is just build up to it. Yeah. Yeah, which we haven't done. Yeah. Yeah.
So is it reasonable to say the hypothesis is that the relationship between latent and acquisition is mediated?
Period. It's just mediated.
It's mediated, right?
By all mediating variables.
By all mediating variables.
That is a reasonable approach. For the remote folks, it is a reasonable approach to not split it up and just say that the effect of the IV is mediated by all mediators currently modeled. But when you do that, you just have to make sure you theorize. All your logic and rationale is following that test. Yeah. Okay, one more chat here. Thank you. You're welcome. Okay. Here we go. So that's mediation. Boom, done. Easy enough. Moderation. There are multiple kinds of moderation. Let's do this first. Let's delete, well, I'm going to save as. Save this, and I'm going to save as multigroup. Save as Causal multigroup. We have a new model we can work with here. And we're going to get rid of these A and B because we're not going to use them. Delete A. Don't delete the line, just delete the label there. B. Okay. Save this again. Okay, we had a multigroup moderator, gender. Let's throw gender in here. It's actually the same as when we did the invariance test. That easy. Not that that was easy. Double click group number up top here. Call it male. Hit new. Call this one female. Or whatever it is your grouping variable is. And hit close. We now have two groups. We need to bring in the data for those groups. Data files. We have data for male already. Let's go get it for female. Yeah, that'll work. And then the grouping variable, for me it's gender. For you it's whatever it is you have. Your data. I'm going kind of fast because this is what we did this yesterday. Grouping value, for me, male is 1. Female is 2. So in the end, it should look something like this. Okay. Okay. And when we run this again, ooh, don't run it yet. Stop estimating a user-defined estimand. So click this and do not estimate any user-defined estimand. Because otherwise it's going to be looking for an A and a B, which we don't have. Do we need to bootstrap at this point? We don't. We don't have to. You can if you want. It's not going to hurt anything. It just takes longer, so I'm going to get rid of it for now. I'm going to not perform a bootstrap. Run it. Now, during our invariance tests in the measurement model, we found partial scalar invariance for, was it anxiety, I think, and playfulness. Just those two. Everything else was fine. So any paths we test across groups that involve anxiety or playfulness are two independent variables, unfortunately. We'll have to just list that as a limitation. Recall we didn't meet full scalar invariance. Okay. So we ran the model. We can, if we hit the up arrow, we can see that it does differ between male and female. If we toggle back and forth here, you can click male, click female, just go back and forth. Like that. That's. Let me zoom in. Let's find a path and just look at it. In fact, we'll look at this end. 42, 39, 19, 03, and these R squares here. Currently, this is for female. This is male. Female, male. Yep, there we go. So they differ. We do observe differences. The question is, are those differences significant? There is a way to test, find out. Save this, now we've got it all set up. We'll do it just like our invariance test. We can go like this. Analyze. Multiple group analysis. And hit OK. And it wants to do all this stuff. That's fine. Just hit OK. It's going to think about it. And it gave us all these models here. So many models. I actually don't want all those models. I really just want to look at the structural weights. That's what I'm interested in. I'm just going to delete everything except unconstrained and structural weights. So this is the measurement weights. I'm going to delete it. This is the unconstrained. I'm going to keep it. I'm going to get rid of measurement residuals, delete. Structural residuals, delete. Structural covariances, delete. And we're back to structural weights, which is what we want to keep. So now I just have two models here, unconstrained and structural weights. And just like with invariance, what that does is it names all of these parameters and forces them to be equal to each other in the structural weights. If I double click this, you'll see all of those parameters are forced to be equal. B15-1 equals B15-2. Okay, close that. And when we run it, we hope that it works. Did it work? It worked. Excellent. Okay. Now when you go out to the output, there's a new section called model comparisons. Click on that. You get one little thing here. And what this says is men and women are not different when it comes to your model. They're the same. It's essentially a chi-square difference test that tests the unconstrained model versus the constrained to be equal model. We're saying with the constrained to be equal model, we're saying men and women are exactly the same with this model. With the unconstrained model, we're saying men and women have the option to be different. Are those two realities the same? And the answer is, yeah, they're the same. So men and women, not so different in this model. This is a global test, meaning it's for the whole model. Since we did not observe any difference, we are not compelled at this point to go and find out where a difference might occur. But as it is our theory, I mean, kind of nice to find a difference, right? So, but what you'd have to do, you'd have to say, globally, this model is not different. We didn't meet our global test, but just as a point of interest, we found a path that was different, possibly. We're very different. So yeah, the R-squares were quite different. Here's my theory on why men and women aren't different in this model. I'm not going to write a book about it in general. But in this model, we only have 91 women, something like that. And so there's a lot of error associated with low sample size. And so while they may be different along the mean regressions or the mean R-squares, things like that, there's so much noise and error in the female population. And again, it's due to low sample size. I'm not making any generalizations about women. But there's so much error in a low sample size that it probably overlaps with the men's regression weights too much to say that they are different. Had we had more women, what that does is it tightens up those regressions and pulls in the error. And we have the men's whose error is already pulled in because they have 200 men. And so it allows them to separate and let their differences shine. Yeah.
Another approach would be take the R-squared for men into acquisition, take the R-squared for women into acquisition, and then do an ANOVA.
Or do a pseudo F at that point. Yeah, you could do it's called a pseudo F, an effect size. You can see R squared, are the two R squares substantially different? Yeah, is our predictiveness for men and women different? Yeah, I wonder, I've never taught this. This is just occurring to me as we go. In my stats tools package, there is a pseudo F calculator, the effect size. And so instead of included and excluded, it would be men and women. So let's do that real quick. So the R square for males on decision quality, I can see this one better. Information acquisition is 41. So put a 0.41 here, 0.41. For females, it is 0.37. 3, 7. And the answer is there's a very small difference between men and women with regards to predicting that variable. Interesting. I've never tried that approach. That's cool. Okay. Let's say we wanted to find a difference. Because it's our theory, we had a specific hypothesis about a certain path that was different. For the sake of the exercise, I'm going to go find out which path is truly the most different real quick. I'm just going to copy out the regression weights tables and find the one that is really separating them. Regression weights, standardized regression. There we go. This is for males. Copy this out. You don't have to do this. You can just watch this part. Yeah. That means there shouldn't be any. So since the global p-value for the chi-square difference test was not significant, there probably won't be any individual local path that's going to be significantly different. So me going and fiddling around down here is really just an exercise for you guys to see how you would do it. Yeah, same idea with Tukey's and Bonferroni in an ANOVA. If the model level ANOVA is not significant, you're not going to find differences in the Bonferroni test. Those who didn't understand that, don't worry about it. Okay. Okay, but this is for the sake of the exercise. Here we go. I want to find the difference. DIFF equals abs of this minus this. And here we go. Let's get the biggest one. Conditional formatting, highlight cell rules, top, bottom, top. Let's do top 2. And the biggest differences we observe are not at that level. Oh, no. I just want the structural. The structural stops here. Delete. Okay, there we go. So the biggest difference is right here, the effect of age on information acquisition. Who'd have thunk? But you know, I'm not interested in that. Yeah, so I'm going to get rid of these controlled effects. Age deleted, experience deleted, and here's experience up here, deleted. Okay, now, most interesting. Social desirability, not interested. So it looks like our controls are the most differentiating thing. Here we go. Decision quality, computes to decision quality. Okay. I'm not actually going to check that one first because look, the male estimate is probably not significant, so there's a lot of error. I'm going to go to this one up here where they're probably both significant. So computes, playfulness to computes. So look at that. Playfulness to computes is this one right here. If I toggle, it's 0.46 for females, excuse me, and it's 0.40 for males. So let's see if that's different. If I do the down arrow, see what these are named, they're B11. What I'm going to do is I'm going to go unconstrain all of them except B11? I shouldn't be asking. I should be telling. I can't remember. I constrain them all except B. The idea is it's actually the same thing from different approaches. I want to say the men and women aren't different on that path and test that against the model where they are different. So I want to just constrain B11, yeah. And then I do a chi-square difference test, and if it's significant, then something. We shall see when we get there. I'm unconstraining everything except that path. Okay, so B11 is still equal. We're saying men and women are not different. Is that different from 0? Is that different from them being different? The null hypothesis is they're the same. They're not different. So if we observe a significant p-value, that means they are different. Got it. It's in my head. It's in my head. It's such a house of cards right now in there. Not stable at all. Or you could do it the other way and then look for a non-significant p-value. Yeah. Correct. Okay, so we're going to test to see if them being equal is any different from them being not equal. And if there's a significant chi-square difference test, then they are different. That sounds so backwards. Model comparison, sorry. And as you theorized, as you predicted, there is no difference at all. We shouldn't find any differences really because the global test failed. But that's how you would do it. Okay. Okay. I'm going to address some chats here. Yeah, you can see if a particular factor has differences. That's a measurement invariance. Okay, let's see. Should we check model fit after creating groups? Oh, the question, should we check model fit after creating groups? The real question is, when should we check model fit? And the answer is, anytime the model changes and you're testing a hypothesis, you must address model fit. Because we cannot rely on any of the results for your hypotheses if we haven't assessed model fit. So the model fit won't be changing unless we change the model. So anytime the model changes and you're testing a hypothesis, you must determine if model fit is good. So should we have done it in this case? Yeah, we probably should have done model fit check real quick. So let's do it. Model fit still good? The answer is yes and yes. Model fit is still good. So yeah, and we should report that. We should say we check model fit again. Here are the chi-square degrees of freedom, RMSEA, P-close, and CFI. Every time you test a hypothesis and the model has changed. We're not testing a hypothesis with CMB. What you could do is in your hypotheses summary table, which a lot of people like including, you could just list another column for model fit during that assessment. Okay. So what are you doing in Excel is to test whether any local specific path is different between gender. Yeah, that's what I was doing. But as somebody pointed out here, is actually an exercise in futility because the global test failed. So if the model is no different across groups, then we're not going to find a path that is. But I just want to show you if you did find a difference at the model level, how could you go find it at the path level? Two things. Before we are done today, will you be building a path model? Yes. When building a path model, is it best to standardize everything on the outside or wait for the until ready for interactions? I will discuss that thoroughly. So we'll get there. Don't worry. Okay. One more. Awesome. Okay. Here we go. So that was multi-group comparisons. Not terribly complex. There it is. Let's go. The next thing is interactions, right? Is that? And that's it. We could finish before lunch. And then after lunch, I could just help you guys one-on-one with stuff. That'd be really great. And you guys don't have to come back if you don't want to after lunch. Let's try to do that because interactions aren't that complicated. Here's what we're going to do. I'm going to save this model because we did some cool stuff in it. We're going to build a path model now for our interactions. But I'm also going to show you how you might do it latently. So maybe I'll do that first. Or maybe I'll just show it. Okay, I'll show you. I'll show you. I'll show you. Here's how you do it latently. So we do interactions. Interactions are the true form of moderation. It's where you multiply your moderator by the independent variables. We theorized experience would strengthen the relationship between playfulness and usefulness, and anxiety and usefulness. Maybe it dampens that one right there. The way we test that is by multiplying experience by playfulness or experience by anxiety. Now, to do that latently goes like so. We're going to go to SPSS. going to go to, really want to do it here. Well, first things first, we're going to go to Analyze, Descriptives, Descriptives. Analyze, Descriptives, Descriptives. And then we're going to pull in everything that is involved in the multiplication. So for us, that's anxiety 1 through 7. Well, actually, is it? I think we reduced it, didn't we? It's anxiety 1, 3, 5, 7. And playful 1, 2, 3, 4, 7. Anxiety 1, 3, 5, 7. 1, 3, 5, 7. And playful 1, 2, 3, 4, 7. I think that's right. 1, 2, 3. So these ones. Oh, and experience. Got to pull in experience because we're multiplying that by everything else. Ah, where'd it go? Over here for some reason. Okay. So we have all these, and you need to make sure to check this box for save standardized values as variables. What we're doing, I'm just having you quick, sorry, I haven't explained it. What we're doing is we're prepping our interactions. Interactions are multiplications of the moderator and the independent variable. But in order to have a new variable, that multiplication, that is not multicollinear with the original variables, you have to standardize before you multiply. And mathematically, it breaks the brain when you try to think about how multiplying first can, or standardizing first can fix it. I was so confused by it. I emailed, what's his face? That one dude, McKinsey. I emailed McKinsey. And just like I get emails all the time, I felt like I was on the other end. And I was like, hey, I do not understand this. And people are asking me about it. And he says, email, like 2 pages long. Here's how it works. I still don't understand it. But it does work. And I've tested it. I've run the tests he sent me, and the results are logical. So on this one, it's a faith-based analysis. So just trust me on this one. It does work. Yes. Uh-huh. Yes, so gender is a moderator. For the remote folks, I'm just going to repeat it. A gender is a moderator where its values are 1 and 2, or 0 and 1. You could actually do exactly what we're doing right now and multiply gender because it's binary. If it were multinomial, you couldn't do this. But because it's binary, you could multiply gender by all these other things and do an interaction, and it would have the same effect as doing a multigroup analysis. The beauty of multigroup analysis is when you have multinomial categorical variables, like religion, right? You have 10 different religions. You can't just multiply those religions by some other variable. You'd have to separate them into their own binaries, and it gets so messy. So a multigroup is really beautiful for that. Roughly, not exactly, because in the last model we were using a latent model. This one we're actually going to use latent too. It's just when you start multiplying latents by latents. Imagine for a moment experience wasn't latent, or wasn't observed, it was latent, and we had like 7 experience items. What we'd have to do is multiply anxiety 1 by experience 1, anxiety 2 by experience 1, anxiety 3 by experience 1, and then do it again for experience 2, and then again for experience 3. And you'd end up with, when you do the permutations, a lot of indicators for a new latent construct, which is why I tend to not do it latently unless I have a moderator that is a single variable. Okay, here we go. We're standardizing to reduce multicollinearity. Just hit OK after you check that box for save standardized values. It just runs some stuff. What it really is doing is in the back end, it creates new variables for us. At the very bottom, we have all these Z variables. These are all standardized. Why does it say Z? Because it's a Z score. Here it is. You can see Z score right here. These are all now standardized, meaning they have a mean of 0 and a standard deviation of 1. And now when we multiply them, we will get what we're looking for. Multiply them in SPSS is a real pain. But here's how you do it. Transform, compute. And you'd say a new variable called Anx1 exp. And you'd multiply over here. Here's Anx1, double click it, multiplication sign, and z-exp. And you hit OK. It creates a new variable called Anx-exp. Exp. Here at the bottom, you see Anx-exp right here. We have to do that for all of them. Can you imagine if we had a latent moderator? It would be like 60 times. And then the new latent moderator would have 60 indicators. Yeah. I'm just going to do this in Excel a little faster. So we already did anxiety 1. I'm going to do all the rest here. Control C. Oh, wait, Control C doesn't work for me over here. That's right. Copy. And if you don't want to do this as well, I'm just going to save it, and you can use my file. Need to remember what these are. These are, I'll go back over here and do it. Copy these. C. So I'm going to go, oops. I'm going to go a little fast here, and then I'll just save this file for you. There we go. Okay, what I'm doing is I'm going to multiply these. We'll see. And actually, I'm going to name these Anx 3 exp, Anx 5 exp. I don't actually need to do that. I'm just going to do it elsewhere. Okay. Equals this times this. Enter. And pull it over. That many times, I think. Let's see, is it that many times? Control C and Control V. And that's what I want because I don't need experience times experience. Here we go. And I'm going to send those all down. These are the new values. Copy that. Stick it over here. Starting with 5, I believe. Nope, starting with 3. Paste. See if it pastes for me today. I didn't do experience. I missed out intentionally. Did I multiple? Oh, I didn't anchor it. Thank you. Oh, this is why multiple eyes are better than mine. Thank you. F2. I'm saying multiply by experience, but experience I2 needs to be anchored. F4. 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 There we go. For those who want to know what I just did, I just made it so that experience stays still. F2. Yep, there we go. And then, so experience stays still now. Again, I'm not expecting you to do this with me, which is why I'm going fast. Thank you for catching that error, because I would have ruined everything. Infinitely more complex. Yeah, we want to do it latently for the degrees of freedom. But they're latent, and so even though we're eating up a new set of, let's say, 7 degrees of freedom, we're supplying a new set of 32 or whatever. Yep. Yep. And they'll be part of a new factor. I'll show you. I'm going to paste them here as new variables. Okay, and then. Okay, we have Anx1. I have to just rename these as Anx3 exp, Anx5 exp, Anx6 7 exp, and play for 1, 2, 3, 4, 7. Play 1, play 2, play 3, play 4 exp, and play 5 exp. All right. 7, thank you. Play 7 exp. Okay. Save the data set. Huh? Yeah, you need to speed up that part. That's right, because you'd be speeding me up. Yep. In my videos, I'd speed it up, yeah. Exactly. 7 of these. Oh, no. What are you doing in Excel? Oh, no, that's different. 2 things. No, we don't have that. You assume. Okay, this one right here, Kyung. You assume that the specific path gender has different effect. When you test, I see you can unconstrain any paths other than that path. Shouldn't it be the opposite? The answer is you can actually do it either direction, and then whichever direction you do it in depends or determines whether you want to look for a significant or a non-significant p-value in the chi-square test. Why aren't you using the factor scores latent variables to do this? I know, seriously. Never mind. We'll do that next. Because I love pain. When we do the correlation table, we should begin without those variables that are standardized, right? Correlation table. Oh, like when you're sticking in the mean and standard deviation and stuff, and the correlation. Yeah, do it with unstandardized would be best. The objective of creating z-scores was to standardize. Yes, correct, and we're doing that so that we don't have to have multicollinearity. When do you recommend doing correlation table? Excuse me. During the CFA. I would do it during the CFA, the end CFA. That's when you do the correlation table. Okie dokie. There we go. Okay. Okay, this is saved. You can pick it up out of the Google Drive folder if you want. And now we're going to go do a latent, disgusting, messy interaction. Here we go. I have to relink the data. And I don't want male and female in here. So I'm going to go back to causal latent initial. Excellent. This model here, causal latent initial. And what we have to do is create a new latent variable with this candelabra thing. And so we'll click, and then it has, we have one with 4 and one with 5. Nope, one with 4, one with 5, yeah. New variables. So 1, 2, 3, 4, and another one. 1, 2, 3, 4, 5. We'll rotate it. Clean it a little bit, move things around a little bit. So it fits. Oops. Just moving things around. Okay. And then we need to put the variables in there by dragging them in. Except I need to link the new data set. So let me save this, link the new data set. Double click the one that's there. Grab the same one as before. Bootcamp trimmed. Did I use bootcamp trimmed? Uh-oh. I was using the _C. All right. All right. That's going to cause a problem. Dang it. Okay, we can use it. Okay, use the bootcamp trimmed _C. Hit OK. How do I get the data files to what? To link? Oh, I just clicked on this one right here, or file data files. This is actually going to break. You'll see it break in just a moment. But let's add these in, and we can make it work. Don't worry. It's just going to break it initially. So click on the white stacky thing, and expand this so we can go all the way to the bottom here. We're going to pull in anxiety 1 into the 4-part one. Anxiety 1, EXP. Anxiety 3, EXP. So on. And then pulling the next set into the 5er. Play. But those of you who have done interactions before, you can see how this is a lot more complex than using a path model with composites. Never done oh, you have? No, it's a mess. Yeah. I'm going to resize observed variables. There we go. Okay, I'm going to name this one. Variable name, this is Anx EXP, not ESP. I'm going to name this one Play EXP. And I'm going to run this and let it break so I can show you a very nice error that everyone would. Thank you. Plugins, name errors, name unobserved. I'm going to correlate them. Yep. No, you're good. You're good. I'm going to correlate them, and we're going to regress. So, covary. I'm not going to do it that way. I'm going to go to select and select all the exogenous variables, including age and experience. Drop covariances. Mess. Unselect. And then I got to draw the arrows from just what we theorized to start. What we theorized was effects on usefulness, right? Okay, so I'll just draw them there. Now we have to check model fit, because what if these are highly related to something else in the model? Our model is now invalid unless we account for that effect. So let's run it. We're going to get an error. There's the error. This is an error many of you will get over the course of your time with Amos. The observed variable useful is represented by an ellipse in the path diagram. So in our data set we're using, which is the _C, we have an observed variable called useful. In this model, we have a latent variable called useful. They say you can't do that. You can't call an observed variable latent. So what I have to do is double-click all of the latent variables and just add a letter. I mean, add an F at the end or something like that. Or F, factor, or just F. I'm just call it useful and compusive and playful and anxiety and social desire, decif, and disqualif, and infoacf. There we go. Now, those are not variables in my data set, guaranteed. But that's how you fix it. Okay, what a mess we have here. I'm going to save as. This is our causal latent interaction. Because we're crazy. Okay. Now we're going to run it. It's running. And it ran. But it's still thinking. Still thinking. Why is it still thinking? It's a really complex model. We've added so many new parameters, which is also why you typically don't do latent interactions in Amos, because Amos just can't handle it. It shouldn't be taking this long. Hello? Oh, while that's running. You have experience as control and running a moderation effective experience. Experience, oh no. That's supposed to be frequency, huh? Let's pretend experience is a moderator. It was supposed to be frequency. This is why you always collaborate. You never write solo papers. Because you make so many, I'm making mistakes and I'm supposed to be this expert. Yeah, it happens. Okay. Oops, sorry, good catch, Kyung. Why adding a letter to the name of latent variable? Say it again, please. It's because all of these variables like useful and anxiety exist in the data set I linked. They exist as actual columns in the data set. But I'm saying in this model that they're latent. There are no variables values And so it says you can't do that, so I have to change the name of my latent variables. That's why I did that. Mamma mia, yes, seriously. Why is there not an error marker on, oh yeah, why are there no errors on our new interactions? Because they're not endogenous. There's nothing predicting them, so they don't need errors. Social desirability needs to be renamed. Yes, correct. And I did, I added an F in there. You can't see it. Okay, it ran. And the question is, do we have interactions? Actually, the question is, do we have model fit? Okay, because even if we have interactions, it doesn't matter if our model fit is terrible. Okay, notice our degrees of freedom jumped way up to 859. Let's go look at model fit. The answer is, hey, CFI looks all right, 0.9. Be close, 949. RMCA, 0.046. We're good. I check SRMR as well, but we're good. And so now we can go look at the interactions. And if we weren't good, we'd address model fit like we've done many times already, so I'm not going to cover that. We go to the estimates. Yeah, we check the SRMR. And if it's good, then we're good. If it's not good, yeah, it's the plugin. Okay, let's go look at the interactions now. Here they are at the very bottom. And the question is, do we, no, not, let's see. Where did they go, where did they go, where did they go? Should be up here. Here we go, at the top of the regression weights table, we have these two interactions right here. Neither of them are significant. That is so common with interactions. No significant effect. So, if one of them was like close, I might delete the one that was less close and see if it changed things. Let's try that right now. Playful experience, just completely useless. So I'm gonna delete playful experience right here and all of its components. And run it one more time and see if it helps. Because it was impotent anyway. Didn't need playful experience. Shouldn't use those words altogether in a sentence. Impotent playful experience. Okay, sorry. Watch myself, I'm BYU, and I'm being recorded. Yeah, each word by itself is totally clean. Okay, look at the output. Look at the estimates. And go find that one, which is right here, angst experience. And the answer is no, still not significant. We have no moderation. If we did have moderation, which is fairly uncommon, but if we did, what we would do is go plot it, which I'll show you right now. Go to the stats tools package, go to the two-way interactions, you name your variables. Our independent variable is, let's see what we have left here. It's angst. Anxiety. If anxiety, our moderator is experience, even though it's supposed to be frequency, sorry. And then our dependent variable, in this case, our dependent variable is useful. Useful, yes, something like that. Okay. And then we put the unstandardized coefficients here. So the effect of the unstandardized, the effect of anxiety on usefulness is, here's anxiety on usefulness, negative 0.094. Negative 0.094. Like no effect. Oh, that's unstandardized, so we don't know. The effect from experience to usefulness is 0.003. And the effect of the interaction was negative 0.05. Negative 0.05. And so you can see it plots these and it shows really there's very little going on here. Very little difference. It'll throw an interpretation in there for you. Experience strengthens the negative relationship between anxiety and usefulness, but it is completely irrelevant because the null hypothesis is supported. There is no effect. There is no interaction going on. So you wouldn't even report this because we don't know if it's like this or if it's totally the same line. And you remote folks, you can't see that, but I guess the word's probably fine. So no interaction. But if we had one, we could copy this and paste into our manuscript. And we could even use that verbiage there. We need to add intercept constant as well. The intercept, in this case, is just an anchor for the graph. So if I put 2, it'll lower it. If I put 5, it'll raise it. So I put 3 because it's in the middle. Really, we're interested in the slope, not the intercept. Gotcha. How should our model look like if we added frequency? I don't know. I mean, well, I know. Your model would have another variable up here called frequency. And instead of anxiety times experience and playful times experience, you'd have anxiety times frequency and playful times frequency. It was, frequency was just one, it was an observed variable, just like experience. If it were latent, we'd have a disaster of a mess on our hands. We'd have to multiply every one of its indicators by every one of these indicators. And so you wouldn't do that. What you do instead is do this in a path model. I also need to address the standardizing issue. Let's do that in the path model. I'm going to save this. What we're going to do next, we're going to create a path model. Okay, would you delete the moderator after proving it doesn't moderate anything? Yeah, you could delete the moderator or the interaction and the moderator, actually. Yeah. Okay, we're going to go to a new model, file new. This one, we need to link the data. It's going to be the _C data. Because that has our composites in it. Okay. And we're just going to pull out each of the observed, the factor scores for our variables of interest. So we still need a control for social desirability. We had anxiety and playfulness over here. As predictors. We have useful as a mediator. And comp use as a mediator. And information acquisition. And decision quality. And we have control variables of experience. Whoa, I'll fix it. Frequency was a moderator. I just messed it up. Yeah. And age. There we go. Okay. So it's the same model as before, but instead of using latent factors, we're going to use factor scores, which makes it far less complex. Let me delete the label on this one. So let's get to that. Just a sec. Plugins resize. There we go. Okay. Notice, I need to pull in the interaction. I need to do the interaction. When you're doing interactions in a path model, you still standardize. Let's do it, and we'll talk as we do it. Okay. We need to go standardize. Let me save this first. So this is path interaction. So this is an interaction path model. But in SPSS, we need to go create our interactions. So we go to transform, compute. Oh, not yet. Not yet. We need to go and look at. I did it for a latent. I didn't do it for the factor scores. What I need to look at, actually, Amos has changed what the algorithm it uses for factor scores. I can't remember if it's standardizing these or not. So let me click on playful and see if it's standardized. I'm just going to do an analyze, descriptives, explore, plots. Don't do this, just watch. Are they all positive? Okay, so then it's just a weighted average. Okay. But just for your benefit, if I were to throw playful in here, this is one of our composite, our factor scores. And I wanted to see if it was standardized already. I can use a histogram, see, oh no, the distribution is not standardized. So I can now go and standardize it. You wouldn't want to standardize a standardized variable. That's what I'm trying to prevent here. Because if Amos had already standardized it for me, and I go and standardize it again, then that's, you don't want to standardize a standardized variable. Yeah, because then it's bad. Yeah, don't do it. Okay, so we can do the standardizing. Let's go ahead and do that. Analyze descriptives. And I'm going to move a little bit quickly. We've already standardized. Well, let's do it with frequency this time. Let's do it right. They'll be roughly the same, but not identical. Yeah, but you're right. We could have done that. I'm going to throw frequency in here. And then we need to throw anxiety. Where'd you go? Playful and anxiety in here to standardize. Just those three. And I realize I'm going fast, but we've already done this, so not like we need to review the steps. I'm going to do this in SPSS. I'm going to compute anxiety times experience. Nope, frequency. And get rid of that. This is going to be the ones we have at the bottom here. Anxiety times frequency. Okay. Do it again. Compute. It's going to be playfulness times frequency. Z playful. That's what it's called. Yep. Z playful right here times frequency. Changes to playful. Okay. We now have two new variables. Z playful times experience and Z or times frequency. Z anxiety times frequency. Save this data set. Go back to Amos. Relink the data set. Even though it says that's the one it's linked to, what it does is it links it pulls all the data into memory. And so if you update the file, it doesn't update memory. Just you got to relink it. Okay, and now for the interaction, we have to pull in these two right here and frequency. Do we have to pull in Z frequency and Z playful and Z anxiety? Nope. You don't. Mathematically, I know. You probably got in trouble. No, good. Good. So I've tried this both ways, where I pull in the Z-scored anxiety and Z-scored playful and Z-scored frequency. I do need to pull in frequency, wherever it is. Here it is, up here. And it actually doesn't matter one bit. The math will be the same. And you'll end up with the exact same estimates, down to the last decimal. Yes, Jagdeep would agree with me on that. Yeah. Yeah. The only ones you have to pull in that are standardized, or well, actually none of them, because these two here, they were standardized before we multiplied. Yeah. Okay. So all the rest are unstandardized. It's just the only purpose of the standardization was before we multiply in order to reduce multicollinearity. That's the only reason we standardize. Everything else can be unstandardized. Okay. Then we draw the model just like before. Speed me up 2 times. Frequency, that's our moderator. It only has to be connected to the thing we are theorizing it is moderating, or involved with. Put this everywhere real quick. You can see why I speed it up in my videos. Not fascinating. So I guess age, actually, we weren't going to have it on anything except info acquisition and decision quality. So I just need to delete that path. Yeah. a mess. Now you see, we're going to get rid of degrees of freedom really fast here. There we go. Then anxiety and frequency need to go on usefulness. Play and frequency need to go on usefulness. They don't need to go anywhere else unless model fit says so. I added a path I shouldn't have right here. I'm going to get rid of it. Then we're going to covary all of those. There we go. What a beautiful mess. Yep, we need to add error terms. Whoa, that's cool. Okay, trippy. I can do that all day. Need to add error terms. Here, 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 and here, because they're being predicted. Name those unobserved variables, and save. We did. Oh, the errors? Yeah, we can covary those errors right there. Okay, so this is the same model we just had up, except with frequency, not experience, but it's not latent. I'm going to really quickly, I'm going to magic clean this. There we go. Okay, and we're going to check in the output, standardized estimates, squared multiple correlations. Check modification indices, because we want to see if our model fit's going to be good. Save one more time, cross our fingers, run it. It ran. Look at the output. First thing, model fit. Model fit's actually good. Notice we only have 12 degrees of freedom, but model fit is good. And our MSEA is it's okay. It's less than 0.08. I mean, the peak close is above 0.05 by just a bit. We can, I mean, if we wanted, we go look at modification indices. And yeah, 1 and 4, I bet it's the mediators, 1 and 4. Yep. So we'll covary those, and we'll be hunky-dory. Yeah, I lost another degree of freedom. We go look at the output, though, model fit. Everything's improved. P close is now way up above 0.05. So we're good. Yeah, we're good at this point. These boxes? So these boxes are calculated based on a weighted average where the weights are the regression weights from the CFA. Yeah. There are numbers behind these now. Okay, so now we need to see, is our interaction significant? We go look for these right here, anxiety, frequency, unuseful, and no. No significance. So, meh, as expected. All that work. Yeah. Okay, how should our model look if we had added frequency? We talked about that. Why you don't want to standardize so why don't we want to standardize a standardized estimate? It's because it's already at a mean of 0 and a standard deviation of 1. It shouldn't do anything, but it does alter the values. And it can, because we'd be wrong. Nice. That's how I should have said it. It could alter the values and cause trouble. So no Z's, or it's better safe than sorry. There's no safety about it. If you use all standardized variables, you will literally come up with the same. I'll just do it real quick. Check this out. I won't use them all. I'll just throw one in there. Look at this right here. I'm going to throw frequency standardized in. Frequency to useful is a 0.25. Easy to remember. Let's change that up. Frequency, I'm going to use Z frequency instead. Z frequency. It was 0.25. Delete that label. Yeah, just right over it. Run it again. Should be 0.25. 0.25. Okay, it's identical. There's no difference. So I'm really glad that worked. Yeah, if you're worried that one of your reviewers is going to want standardized, either beat them down with scientific logic or just do what they want. Yeah. I lost a step. Use frequency as a moderator, not as a control. Correct. Oh, somebody says gotcha. Okay, got it. Okay, good. So, I think is it. Let's just check here. Let me check here. We bootstrapped, and I talked about that was for mediation. We did a mediation. We talked about moderation. There are different types of moderation, multi-group or interaction, which we talked about. The slides are really just FYI. Determining significance of moderation. Here's a video for it, but also we did it. Multi-group moderation, we did. Interactions and how to do it, we did. Here it is. Controls. We've talked about controls the whole time. Controls are things we need to control for. Anytime you're talking about firm performance, for example, you have to control for firm size, period. Because firm size is the greatest predictor of firm performance. It's not theoretically interesting anymore, but you have to control for it. Anytime you're talking about health, you got to include parents' health, things like that, medical history. You got to control for that. But you just treat them like independent variables. We did this. Here's some recommendations from that reference. We talked about that. Exercises, extra time. We did. I want to show you one last thing. Two last things. Yes. Yeah, so the controls, we did measure frequency. It was on the survey. Okay, here's the last-ish thing. And then what we're going to do, we're going to be finished with the whole boot camp by lunch, so that if you don't want to come back after lunch, you're good. If you do want to come back after lunch, I will be here, and I will work with you one-on-one, and that applies to remote folks as well. That's totally fine. And I'll be here at 2. I'll log in to Zoom and see if anybody's there. If nobody's there, I'll keep Zoom off. And if nobody shows up back to the room, I'll go take a nap. I'm tired. Okay, 2 things I want to show you, and then I'll look at the chat. In SPSS, you can do something pretty cool. You can split a file. I went to data, split file. And you can split your entire data set along any variable. Let's choose gender for ease of explanation here. Here's gender. I'm going to compare groups on gender, or you can organize output by gender, so that anything you do after this, if you run a regression, if you run an ANOVA, if you run anything, it will separate it by that variable. So I'm going to do a compare. I like compare. Hit OK. Nothing happens really. But if I now go run a regression, let's see, regress, where are you? Linear regression. Yeah, this regression right here. How about that? Run it. Check this out. I have 2 models, a male model and a female model. And here are the R-squares for each. And here's the significance of each model. And here are the regression weights for each. And so I can compare on that through any analysis I do. Now, if I went and tried to do an ANOVA using gender as my factoring variable, it wouldn't work, because gender is already split. So I'd have to go reset it. No, it's just a in-memory sort of thing. As soon as I close it, it's gone. It didn't change the data set at all. Yeah. And I could go back and go to split file and hit reset, and it just ignores that instruction. You can also take a variable like frequency. Let me go show you frequency. Here's explore, playful. Let's go to frequency. Throw that in there. Hit OK. Here's frequency. It's on a 1 to 8 scale. Let's say I want to split that down the middle. Age would actually, well, we have so little age, maybe not. But let's say we want to split this down the middle. You could go to transform, rank cases. Throw frequency in there. rank types, n tiles, get rid of rank here, n tiles. Do I want 4 groups or 2 groups or 3 groups? Let's say I want 3 groups, 3 equally distributed groups. Hit continue and OK, and it's going to create, if I go back to my data set here, it's going to create a new variable down at the bottom called n frequency with 3 groups. And if I were to go look at that, explore n frequency, here's what the new set of groups looks like. I have a group, where's the frequency here? Oh, here it is. You have 3 groups. The largest group is from 2.5 and up. Smallest group is 1.5 to 2.5. But it splits them in 3 equal intervals. You do that with age, income, whatever, and then use that new variable as a multi-group variable. And that's a new variable in the data set. Okay, I'm going to get to the chat real quick, and then we're done. Standardized regression weights must be between -1 and +1. Correct. I believe not, because standardized is the number of standardized deviations. So that's confusing. There's standardized variables. That's where the standard deviation is 1. And then there's standardized regression weights. That's where the maximum and minimum are plus and minus 1. And you covariate the controls with the IBs? Yes. Will be here. Can you split across mean or median? This one splits across, well, percentiles. But you could split it at the median if you wanted to do it 2 n tiles. Okay, I'm going to close this. I'm going to stop recording. I'm not going to record this afternoon. I will upload this as soon as